Okay, we're almost ready to start. Let's give it a few more seconds. Okay, cool. Okay, I think we can get started. People can hear me, right? Just to make sure. It was working earlier, but now it's still working. That's good. Okay, so this is our penultimate, second to last lecture for digital design and computer architecture this semester. And we're going to hopefully cover two topics, prefetching and virtual memory. These are both very important topics in modern systems, prefetching clearly for performance and virtual memory for programmability and ease of use and protection and security, as we will see. We will not be able to do a very thorough treatment of prefetching, but I'll give you the basic ideas, hopefully. It'll be fun. And if you have to point to something that can be improved greatly in existing systems from a performance perspective, prefetching has a lot of potential to improve. There are a lot of very good prefetchers in existing systems, but because memory latency is so high and we need the data and we don't want to access memory to get the data, as we discussed multiple times in the last few lectures, there's a lot more potential in prefetching. It's a very rich area of current and future research. That's why it's a very important topic. So I wanted to cover it so that you have an idea. And it's also a very general topic. It's not just in a single done in a single node, but you can do it across systems, across the internet. For example, if you want to not access some other server or some other place for data, you prefetch the data so that you don't see the latency of it. Okay, that's the basic idea. We will build up to it. I'm going to cover some things that we covered earlier just to jog your memory so that we can get to prefetching. Okay, these are readings for this week and last week. Some of them are redundant with what I showed you last time. I also added an example prefetching paper, which we will briefly cover. This is a shorter version of what we will cover. And prefetching clearly has a special place in my research agenda and heart also, because I did my PhD on the topic of prefetching, and I will get to describe to you an idea that we developed in my PhD that went into real processors, and we will also see examples of it. And as I said, it's still a rich area of research, and there's a lot more to do on this topic. Okay, recall we've been talking about memory hierarchy in the past few lectures, and it's perhaps the most critical component of systems today because we've optimized the processor, CPU, computation cores a lot, but the memory hierarchy is very important and main memory is slow. And we've discussed this. We built these memory hierarchies, and we talked about managing the memory hierarchy. And prefetching is actually a method to manage the memory hierarchy as well. So you can think of prefetching. Prefetching is essentially the ideas, as I told you before, is to bring the data before it's needed to the processor, right? And you can manage the memory hierarchy using this prefetching principle. Try to predict what the processor is going to access from main memory or the L3 cache or the L2 cache, and then bring it to a cache level that's closer to memory, ideally registers at some point, right? So prefetching is very tightly integrated with the memory hierarchies today, and you can see it as another mechanism to manage the memory hierarchy. We didn't explicitly call it out when we talked about caches, but you could also integrate prefetching into the caching mechanisms as well, as we will briefly discuss when we get into the prefetching. And you remember this picture, I've shown you multiple times. I'm not going to show it again. And these real processors have deeper and larger cache hierarchies. They're visible. But what's not visible in this picture is the prefetchers that they employ also. There is aggressive hardware prefetching as well as software prefetching that's employed in these systems. Like Apple M1 actually has interesting prefetchers that are not really disclosed to the public, but you may actually find out some information about them on online blogs, for example, or patents potentially. But certainly there's a lot of effort that goes into designing prefetching mechanisms to manage the cache hierarchy in a modern system. And I'll give you some examples of it. AMD Ryzen is another example. Clearly, cache hierarchies are becoming larger, but prefetchers are also becoming more and more important in these hierarchies. And I've already given you examples of Power 10 and NVIDIA as well. Okay, so let's cover what we covered in the last lectures. Basically, we talked about caching, and in the last lecture, we talked about how to improve the basic cache performance. We talked about advanced caches, and we said that there are three fundamental goals in managing caches. We want to reduce the miss rate, we want to reduce the miss latency or miss cost, and we want to reduce hit latency or hit cost, basically. And prefetching actually can help with the first two very significantly. Potentially, it can help with the hit latency also if you're prefetching into the register file, for example. But certainly prefetching, but preloading the data into the cache before the processor actually issues a load for it, you can reduce the miss rate that the processor sees. You can reduce the miss latency also because the processor may actually need the data while the prefetch is in progress from memory, for example. It's not completely in the cache yet, but it's being brought into the cache from the main memory. Then you're reducing the miss latency or miss cost by prefetching. So certainly prefetching can affect these two fundamental goals, two major fundamental goals over here. And as we discussed last time, both three together affect performance. So now think about how prefetching can actually integrate to this as well. And just to jog your memory, we talked about many different methods to reduce miss rate and reduce miss latency and cost that were not prefetching. And hopefully you remember, we talked about more associativity, for example, better replacement insertion policies, software approaches like loop tiling, blocking of loops or blocking of data so that you operate on your working set fits into your caches, right, as we discussed, or loop interchange, if you remember, such that your access patterns are more cache friendly. So we talked about a lot of approaches last time. We also certainly talked about multi-level caches, critical word first, sub-blocking, sectoring, etc. And these are some of these are effective for reducing miss rate. Some of these are effective for reducing miss latency and cost. And prefetching actually is effective at both, as we will see. Okay, as I mentioned last time also, there's a lot more cache optimizations. This is a very rich area that people are working on, and it's increasingly going to be important, as we've discussed multiple times. So if you're interested, you can certainly watch the videos from past lectures. We also talked about multi-core issues in caching, which makes caching even more important, caching and prefetching and memory system management even more important, because you have now more agents or more processors accessing the memory hierarchy. And again, this is called multi-core. You can think of multiple processors, multiple threads, but also many accelerators, like we showed in the Apple M1 chip, right? You have multiple different accelerators potentially sharing cache with the cores, right? Remember the system level cache in the Apple M1 in the earlier picture? That is shared between different accelerators and the core, GPU and CPU, for example, and the vision accelerator and the machine learning accelerator, potentially. So all of these different computational units share the memory system. And as a result, you have even more pressure on the memory system when you have more computational units trying to get service from the main memory system and the cache system. And as a result, caching, prefetching, and all issues related to memory system actually become more important in multi-core, as we discussed in the last lecture. Just to jog your memory, we talked about one particular aspect of the design space in a multi-core system, private versus shared caches. And we discussed the advantages and disadvantages of this. I'm not going to go over this again, but private cache belongs to one core, shared cache is shared by multiple cores. And clearly there are advantages and disadvantages to this that we discussed in the last lecture. And I would recommend looking at the last lecture if you forgot or if you have not attended. And there's a lot more issues that we said, which we're not going to talk about. And these are left for future, like master's level classes or seminar level classes, where we discuss a lot of interesting issues on cache management in multi-core systems or heterogeneous systems, different approaches like software versus hardware approaches, and also different ways of managing the cache, like better predicting reuse, different methods of predicting better what will be reused, what will be needed into the future, or what you should compress and what you should not compress so that you can better manage the cache space. Again, we're not going to talk about that now, but there's a rich body of knowledge as well as research going on in all of these areas. And I'd recommend you take a look at them if you're interested. And these are all issues that industry is tackling as well, like quality of service, aware memory systems. How do you provide quality of service to different cores when they're sharing different levels of the memory system with each other? How do you ensure that one core does not deny service to another core? We discussed this actually in one of the mysteries that we talked about in the first few lectures. memory performance attacks, if you remember. And I'd recommend thinking about it from that perspective now that you learn more about the memory system and the DRAM system. How do you potentially prevent memory performance attacks or denial of service issues? You can also think of these as quality of service problems. If one thread or one process delays another process significantly because it's basically thrashing the cache for another process, how do you actually prevent that? And we discussed how to prevent it in the last lecture. You can control the sharing, right? You can basically say, okay, this process or this program or this hardware context or this thread is going to get this level of cache or this amount of cache, regardless of what else is going on in the system. And that is called partitioning the shared cache, for example, if you have a shared cache, or providing a private cache if you don't have a shared cache. And that certainly provides some sort of quality of service, but it's very hard to do that at all levels of the memory hierarchy. In the DRAM system, for example, it's very hard to partition the DRAM system such that each thread or each hardware context gets enough memory bandwidth, because today's systems are usually memory bandwidth limited, as we discussed, and we discussed the reasons for it also when we talked about the memory hierarchy, because you need to go off chip. And off chip, you have limited bandwidth, and because you don't have enough pins, because you're limited by cost of pins and the cost of the system. As a result, it's very difficult to partition the main memory, for example, or even a very large cache, because it's a costly resource, right? Partition or dedicate some amount of main memory to different processes or programs or hardware contexts. So the question becomes, how do you actually manage the quality of service? And there are many, many interesting questions here, which we are not going to tackle in this course, but which real system designers tackle, both at the hardware and the software levels. Because if you provide how do you provide the support for partitioning and isolation and quality of service in the hardware? And how do you expose that to the system software, such that the system software does a good job of providing service level agreement guarantees, for example, in a data center? Or in a system like a cell phone, you have some implicit service level agreement guarantees that you provide to the user, right? If you don't provide good service to interactive applications that the user expects quick responses from, then basically you're violating some service level agreement, and people may not buy your hardware or software going into the future. So these issues are actually real issues, critical issues, but we just don't have time to cover them in the context of these lectures, because we have only 2 left, as you know, well, less than 2 left now. But I would recommend taking a look at issues like this, and these are some resources that you can look at. Okay, I will cover one more issue that we covered really at the end of last lecture, and this is not going to, you're not going to be responsible for it. I also said that, but I would like to cover this again so that you're familiar with it, and you may have seen parts of this in parallel programming as we discussed. But again, we're not going to go into the details of cache coherence, but cache coherence is an important problem also that exists in a multiprocessor or multi-core system, where different cores have different caches that are private to each other. Basically, the question is, if multiple processors have different caches, and if they cache the same cache block, same address, how do you ensure that all of these processors see a consistent state across that cache block, essentially? And I gave this example last time. Recall, we have this cache block X in main memory. Its value is 1000. Let's say processor 2 loads that value into its cache, 1000. And then processor 1 loads that value into its cache, 1000. Okay. Now, both processors have cached the block in their private caches. Now, let's say processor 1 writes some other data value into that cache block, makes it 2000, let's say. Then the question becomes, when the processor 2 actually loads the same cache block, what value should it load? And just basic consistency, basic happen before relationship on these cache blocks, based on what we know right now, tells us that processor 2 should not load 1000. And if you reason that way, then you're reasoning based on the global view of the system. And you're saying, oh, I know what happened before. Basically, processor 1 actually wrote 2000 to this cache block before processor 2 tried to load the now stale value. So it should not load 1000. Because if you actually make it load 1000, you're making it extremely difficult to provide synchronization between these 2 different processors. And if you really want to know what that is, you really need to take the advanced lecture, or maybe you covered in parallel programming, I'm not sure. But basically, this processor should not load 1000 because these caches are supposed to be invisible to the programmer, right? Basically, basically, the fact that you would be getting an inconsistent value is because there are caches here, and processor 2 is not seeing the update that processor 1 made to this cache block, because each of them independently cache the same cache block without being aware of the fact that one is updating the cache block in a particular way. Okay, so basically, a system that provides cache coherence should make sure that processor 2 does not load 1000. And then the question becomes, who should ensure this, right? If it turns out you could actually do this in software with virtual memory based protection mechanisms that we will discuss in the next part of this lecture, but it's very costly. But many modern systems provide hardware support so that processor 2 actually gets the correct value, or at least it eventually gets the correct value. And that's the idea of a hardware cache coherence protocol. Basically, when processor 1 writes 2000 to this cache block, what it can do is it can broadcast that it is updating the cache block, and another cache that can see that broadcast, any cache that's connected to this network can see that broadcast and can basically say, oh, I have that cache block in my cache, so I'm going to invalidate it. That's one. That's an invalidate-based protocol. Or I have that cache block in my cache and they're broadcasting the value, so I'm going to capture the value and update the value so that it's going to be 2000 from now on. So these are two different methods of cache coherence, update-based or invalidation-based. And we showed an example, invalidation-based coherence scheme very quickly again. Essentially, the idea is all caches snoop or observe each other's write-read operations to the cache. If a processor writes to a block, all others invalidate the block. It's an invalidation-based protocol, and I'm not going to go through the details of it. You're not going to be responsible for it anyway. But basically, the key thing to know over here is if a cache has the block as valid in itself, and if it observes a bus write, meaning bus write signal is asserted when some other processor is writing to this block, then it transitions that block to an invalid state. Okay, that's the idea basically. This transition is the key transition. Of course, there are other transitions in the state machine when you're loading the block, for example, when you're reading it from the memory, you assert a processor read, and you also send a bus read to all of the caches, and the data may come from some other cache, for example, not memory, and then you bring the data into the valid state. So this requires some assumptions, as I mentioned in the last longer part of the lecture, and you can read those assumptions and you can watch the longer lectures. So basically, there are a lot of design issues in cache coherence also. Do you do invalidate? Do you do update? How do you design the protocol? Do you just have only two states like this? This is actually not what is implemented in real systems today, because these two states are too costly in terms of bandwidth and performance. So you implement a more sophisticated protocol. And then the question also becomes, what do you do to main memory? When do you update main memory, etc.? There are many, many interesting questions here, which we're not going to tackle. But if you're interested, you can look at the cache coherence lectures that we provide. And you can see this is one of the state machines that is implemented in Pentium Pro, for example. It's a MESI protocol, which was developed in the 1980s. And it has 4 states, as you can see. And it's a carefully designed protocol to minimize the updates that other caches need to see on the bus, and also updates the memory needs to see. But existing protocols are actually more sophisticated. You may have more states so that you can optimize. But if you really want to know the advantages and disadvantages of more sophisticated protocols, I would recommend looking at these cache coherence lectures. And consistency, memory ordering is a related topic, but orthogonal topic to cache coherence. And memory ordering is also critical for providing synchronization support in multiprocessors. Again, it's a memory related issue. When you have multiprocessors and they share memory, how should they see the operations? How should each processor see the operations done by read-write operations done by other processors? And the idea in a very simple form of memory ordering called sequential consistency is that every processor should see the same global order of operations, so that you can build synchronization primitives like flags on top of this. And if you're really interested in this, you should take a look at future lectures or take the class where we talk a lot more about memory consistency. Okay, so hopefully this gives you a perspective on how important the memory system is, and how rich the problems are in the memory system beyond what we have been talking about and beyond what we're going to talk about. And clearly, cache coherence and consistency are interesting issues. Prefetching affects them as well. I'm not going to talk about them. We do talk about them in the advanced lecture. But keep this in mind when you have cache coherence and consistency issues and you're prefetching data early into the caches. How does that affect cache coherence and consistency, etc.? If you prefetch wrong data, for example, that you're not going to need, you may actually cause coherence misses for some other caches potentially, right? Or you may actually cause other traffic for some other caches, and that may actually be problematic. Okay, so with that backdrop, let's go into prefetching in a little bit more detail, and then we can, so that at least I can give you the basic ideas, and you know this important topic that's been keeping many people busy in the world. And the idea, as I said, is very simple. You fetch the data before it's needed by the program. That's why it's called prefetch or preload. Prefetch is more commonly used term today, but preloading is also used. And this is a general idea again. It's not just related to processors. It's related to system software also. Software can do this also, right? Whenever you write software, you can insert mock load instructions that prefetch data into your caches because you may know how the caching is done. And as a result, you can actually improve the performance of your program. As we discussed in an earlier caching lecture, your web browser can do this, right? It can prefetch the links on a web page that you're visiting, speculating that you may actually be clicking on these links. It may become sophisticated and may learn using machine learning methods, for example, to figure out what is an important thing to prefetch and what is not an important thing to prefetch based on your past actions. In fact, using machine learning related machine learning principles to guide the prefetcher is a really interesting topic of research as well as implementation today in real systems. Windows, actually, a version of Windows had a prefetching mechanism that's guided by machine learning principles. Even about a decade ago, what they used to do is they tried to learn based on the user what program they're going to launch at a given point in time, or based on the pattern of usage. And they would prefetch some of those programs early on into the physical memory of the system, so that when the user actually clicks on that program and loads it, the loading of the program is actually much faster than bringing the program from the disk because they've already done it early. So you can see that prefetching is a very general idea and it can be employed in many systems, including distributed systems as well. But we're not going to talk about that. We did talk about distributed systems a little bit, if you remember, in the last lecture where we talked about advanced caches, because in some of the modern systems, the memory hierarchy does not stop in a single node. The memory hierarchy continues in the distributed system. You may have a storage node where you actually have disaggregated memory, part of your bigger memory space and bigger storage space in maybe somewhere else in the data center. And whenever you actually, if you want to expand your memory capacity, you may actually reference that remote memory node or storage node, so that you can actually have the illusion of a huge memory capacity in the order of terabytes, potentially petabytes, right? So certainly you can think of the memory hierarchy spanning the network also with an interconnect, with a long interconnect in between. Okay, so clearly, why do you want to do prefetching? Because memory latency is high. If you can prefetch accurately and early enough, you can reduce and eliminate that latency. And clearly, memory latency is even higher if you want to access a remote memory and remote storage node to bring the data into the processor that needs it in this particular node, right? So as you expand the memory system to span a distributed system, your memory latencies become potentially even higher. And prefetching becomes correspondingly even more important, actually. Okay, so the huge advantage in prefetching is it can eliminate compulsory cache misses. Basically, the program may have never touched, and this is the huge difference between caching and prefetching. Certainly, prefetching is proactive. Caching is reactive, right? In caching, you need to see, basically, the basic idea of caching is after you reference a memory location, you keep it close by the processor. And that's reactive by definition because you have to see that reference to that memory location. In prefetching, you don't have to see, you don't need to have required that memory location before. You basically guess, oh, I'm going to need this memory location potentially, so let me get it into the cache or into a buffer. It doesn't have to be the cache also. This way, you can eliminate compulsory cache misses. You don't have to see the cache miss at all. So you can completely eliminate all cache misses actually this way. There's a rhetorical question over here. Can it eliminate all cache misses? And remember, we classified cache miss into compulsory, capacity, conflict. Compulsory is the first reference to a cache block. And you can eliminate that with prefetching. Capacity misses, you can also eliminate. Conflict misses, you can also eliminate with prefetching. Basically, you just need to accurately predict the access pattern of the program such that you get the data just before it's needed by the program. As long as you can do that, then you can eliminate any kind of miss, including coherence misses. But you may have actually lost the data in your cache because some other processor needed to write to it. As a result, it invalidated your block. But then in your next reference, if you can predict that you're going to reference the cache block again, you can bring it into your cache before it's needed. So all of those misses can be eliminated. But of course, for it to work well, it involves predicting which address will be needed in the future. And you have to do this well. If you don't do this well, then you may actually be generating a lot of unnecessary requests, which may actually destroy your both performance and energy efficiency because you're wasting bandwidth. And you're also bringing data into potentially caches or buffers that may be used for other blocks that may be more useful, right? So there's one question, maybe it's related to what I just said. Couldn't prefetching lead to severe vulnerabilities? I guess it depends on what you mean by vulnerabilities. If you mean by security vulnerabilities, yes, potentially, certainly. Any kind of speculation today, as we know in the example of Spectre and Meltdown, right? Any kind of speculation can lead to vulnerabilities, but you're not supposed to be able to prefetch data that you don't have access to. That's the key, basically. But that doesn't mean that someone else may not be able to leak the data by constructing a program that guesses what data you have. So certainly, it can lead to side channel or covert channel attacks that we discussed earlier in lecture 2 or 3, if you remember. And any kind of speculative execution will lead to that, including the speculative execution that we saw using branch prediction and out-of-order execution in modern processors. But that needs to be solved in some other way because it's so important. Prefetching is so important for performance, and it's an important research area right now today, actually, to figure out how to get the performance benefits of all of these mechanisms that require speculation without causing the vulnerabilities that they cause. So I think the jury is still out, and there's a lot of research going on that topic right now, which is an exciting area for sure. But I'm not going to talk about the vulnerabilities because at this point, we don't know how to solve them. But there are some solution directions, but we don't have time to discuss that. For that, I think you'll need to take the advanced courses and the seminar course where we discuss actually a lot of these attacks. Okay, very good question. So aside from vulnerabilities, it can also destroy or reduce your performance unintended if you don't do a good job in prefetching, right? If you're predicting the addresses incorrectly all the time, you're basically bringing data that you're not going to use into your caches, and then you may be destroying the good locality that you have in your caches otherwise, for example, right? So this works, of course, if you can predict misaddress patterns in your program, and if you can guess what address you're going to need before you need it. So the good thing is it doesn't affect correctness. It may lead to performance issues if you do something wrong. It may lead to security issues, potentially, side channels. But it doesn't affect the correctness of the program, at least, because if you mispredict the address, basically, you either load the data from a location that you're not going to use, or you basically try to load the data from a location that you do not have access to, in which case you're not allowed to do that anyway, based on the mechanisms that we're going to discuss in virtual memory. As a result, you're not going to use that data. So there is no need for state recovery. So this is different from branch misprediction or value misprediction, for example, where you really need to recover the state if you mispredict a branch, because you have to roll back and go from the correct path again. So prefetching that has that advantage, in fact. Okay, let's talk about basics of prefetching a little bit. In modern systems, prefetching is usually done in cache block granularity because, as I said, prefetching is tightly integrated into the caching system, which we've discussed extensively. And as we said, prefetching is a technique that can reduce both miss rate and miss latency. It can be, it's a very rich area because it can be done by the hardware, compiler, programmer, and the system, or a combination of all of them, actually. In existing systems, all of them do some sort of prefetching, and in a cooperative manner also potentially between the hardware and the software. So this is just one example. This is based on an early paper that I wrote during my PhD. I still like this figure, but basically this is at the time a memory hierarchy, as you can see, L1 cache, I cache, D cache, L2 cache, and the memory controller. At that time, memory controller was off chip, as you can see. Today, many memory controllers are on chip, but with some trends in systems, potentially we may have both off chip and on chip memory controllers again in the system. I'm not going to talk about that, but people are trying to actually make memories more disaggregated. So you may actually have memories that are memory controllers that are off chip as well going into the future. But the point in this slide here is to say that prefetcher can be placed in some level of the hierarchy. And this is an example prefetcher. It's called a stream prefetcher. We will see an example of this. Basically, it observes the requests that are coming into the L2 cache. And basically, it also observes what is missing in the L2 cache. And then based on that, it generates prefetches into the memory system, right? Basically, it's based on the access patterns it sees, it predicts that, oh, I'm going to need this. For example, if it observes that requests are going to cache block A plus 2, A plus 4, A plus 6, A plus 8, A plus 10, at some point it may decide, oh, my stride is 2. So what I'm going to do is, before the processor requests A plus 12, A plus 14, A plus 16, A plus 18, A plus 20, I'm going to generate a bunch of requests to the memory system such that they will be loaded into the L2 cache, for example, just like any other request, but these are prefetch requests that are not requested by the processor itself. So you get the idea, hopefully, right? It can basically have a stride detector, for example, at the cache block level. It can do something else also, which we're not going to go into right now, but there are many creative algorithms people have developed. Predictable access patterns are usually easier. For example, if you're streaming through a memory, if your stride is 1, that's easy. If your stride is n, that's easy. If you have multiple strides, for example, if you're alternating between stride A and B, and your stride is A and then B, A and then B, A and then B, A and then B, many existing prefetchers actually capture that sort of patterns that are repeating. And that's nice, I think. So it's you can think of a prefetcher as a pattern detector in the address stream, in the cache address stream that it's observing. So you can also imagine having a prefetcher between L1 and L2 levels. You can also imagine having a prefetcher in the memory controller level and caching data over there. In fact, many systems have that. So basically, prefetchers can be anywhere in the memory hierarchy, and existing Intel systems actually have many different levels of prefetching today. That's true for other systems also. I just picked up Intel systems because there's more written about it. Okay, there are 4 big questions in prefetching, actually, which we're not going to go into detail on, but I'm going to give you examples of. So what, when, where, and how. So what is basically, what addresses do you prefetch? This is the address prediction algorithm. It's also called the prefetching algorithm. When means, when do you initiate a prefetch request? How early? So basically, ideally, you would like to initiate a prefetch request such that the data arrives just before the processor needs it. Not too early, not too late, just on time. If you're too early, you may be actually evicting some other cache blocks that may be used, right? If you're too late, clearly you're not covering the full missed latency. If you can do it just on time, then you're answering the when question well. So this relates to the timeliness of the prefetcher. And it's not easy to get right, by the way. Where means, where do you place the prefetch data? Do you put it into the caches? Then the question becomes, which cache level? Or do you put it into a separate buffer? Where does that separate buffer reside? So there are many questions over here. How do you keep that separate buffer coherent with the caches in a multi-processor system, or even in a single processor system? So there are many questions. And then there are actually multiple where to place the prefetcher, which level in the memory hierarchy. I showed you an L2 prefetcher earlier, but as I said, it could be multiple levels. So there are actually multiple other where questions that I'm not asking over here, but these are the 2 major ones. And then how is also very important, because how relates to how does the prefetcher operate and who operates it? Is it the software? Is it the hardware? Is it an execution or thread-based prefetcher? We will talk about an example of it. Is it cooperative between software and hardware? Is the hybrid of all of them or multiple of them? And usually in existing systems, it's all of them, a hybrid of them today. So it's a very rich area, as you can see. How do you and clearly, how does the prefetcher operate has very important implications on what, when, and where as well. Because, for example, if you're running a thread to do prefetching for some other part of the program, then what addresses to prefetch becomes easier, especially for difficult to predict addresses. And I'm going to show you an example of this. Okay, let me give you two examples of these questions. So what is an important question? What addresses to prefetch? So clearly, it's important to decide what to prefetch because prefetching useless data wastes resources. It wastes memory bandwidth, it wastes cache and prefetch buffer space. It causes energy consumption on interconnects clearly. And all of these could be utilized by demand requests or more accurate prefetch requests. So you should really be accurate in your prefetching. So accurate prediction of addresses is important. And prefetch accuracy is defined as the number of prefetches you send and what fraction of them are used essentially out of all the prefetches that you sent. Clearly, you want to increase it. But then if you try to increase it, maybe you're not covering a lot of your cache misses, meaning you're not sending a lot of prefetch requests. So there's a fundamental tension between accuracy and how many prefetches you send out. You can be very liberal in sending out prefetches and your accuracy may drop, but you may actually be capturing a lot of the cache misses such that you're reducing, the processor is not seeing those cache misses. But of course, this may come at the expense of memory bandwidth and etc. Now, if you have idle memory bandwidth, and this is good, maybe you're using the idle memory bandwidth for prefetching, but if you don't, then this may lead to a problem. So how do we know what to prefetch? You can predict based on past access patterns, or you can use compilers' knowledge of data structures. You can use programmers' knowledge of access patterns also if you're doing it at the program level. So there are many, many questions over here also. And prefetching algorithm in the end determines what to prefetch. And there are many, many prefetching algorithms that people have devised. I'm going to give you some examples of it, but if you really want to learn more examples, I would recommend taking the advanced course and reading some papers that I recommend. So this is the how part. Basically, how do you do the prefetching? Here we consider three types of prefetching: software, hardware, and execution-based. So software, for example, instruction set architecture can provide prefetch instructions. In x86, for example, there are special prefetch instructions. Many ISAs have this. And the programmer or compiler inserts these prefetch instructions at appropriate place in the code, such that the data is fetched before a load needs that data. So usually this works well for regular access patterns like array accesses, as we discussed in vector processing, SIMD processing, right? But it's much harder to make it work well for irregular access patterns like linked data structures, for example, or graph traversals where you don't have a regular access pattern. So for random access patterns, you can forget about this sort of prefetching, and maybe you can forget about prefetching at all, except execution-based prefetching can be very helpful for random access patterns because you're actually executing the program, as we will see. Hardware prefetching, hardware monitors the memory accesses, as I showed you earlier. It either memorizes some of the access patterns or finds patterns or strides, and it generates prefetch addresses automatically based on what it has seen in the past. And clearly, this has been extremely successful. There are many reports that show that hardware prefetching improves performance significantly on many workloads. And I think Apple M1 is also a good example where hardware prefetching has improved performance significantly. And you can take a look online for that. Execution-based prefetches are very interesting because they're a combination of hardware and software, I would say. Essentially, you execute a thread speculatively to prefetch data for the main program. And this thread can be generated by either software, programmer, or the hardware completely dynamically. And we're going to look at examples of this. Actually, one particular example that I developed during my PhD thesis, as we will see. But before I go into that, let's take a look at a simple hardware prefetcher that does streaming access patterns. So this is directly copied and pasted from this beautiful paper written by IBM folks in IBM Journal of Research and Development in 2002. This is one of the earliest multi-core machines. It's called Power 4. And basically, they have a very nice description of their hardware data prefetch engine, as you can see over here. And the idea is basically it's just streaming prefetcher. At least they describe the streaming nature of it, but I think it's more sophisticated than just streaming. But you can see that the processor is accessing, in a streaming manner, cache blocks. Every time you have a stride of 1 across cache blocks, whenever you access I0 or line 0, L0 through L20. And basically, they have prefetchers across the memory hierarchy that bring data that see this pattern. And basically, they bring data from L2 to L1, L3 to L2, and memory to L3. For example, if you look at L3 access pattern, L3 needs to supply the data I5, I6, I7, I8, and then it supplies I9, I10, I11, I12, and then it supplies I13, I14, I15, I16. And while that's happening, memory can actually also provide the data into the L3, as you can see. Right. So you can also read the paper, but basically when load instructions miss sequential cache lines, either ascending or descending, it could be going the other way also in memory, the prefetch engine initiates access to the following cache lines before being referenced by load instructions in order to ensure that the data will be in the L1 data cache. Data is prefetched into the L2 from the L3 and into the L3 from memory. And they say basically they support 8 such streams per processor. So that's a multi-core engine. So per processor, they support 8 such streams. So if you're operating on 8 arrays concurrently in a similar manner, you can be basically prefetching those 8 arrays. And I'd recommend looking into this if you're interested. Existing Intel processors have even more sophisticated examples, but Power 4 is relatively old. Many existing processors have actually similar sophisticated prefetchers. And this is an early paper that actually introduced the idea of stream prefetching in a similar manner. And if you're interested, I'd recommend looking into it. And I like this table from this paper. This paper was written in 1990, as you can see, by Norm Juppy, who actually is the chief architect of the tensor processing units right now in Google, for example, which we have discussed in earlier lectures. But you can see that they basically show that the cache miss cost is increasing. So this is very well known, as you can see. At that time, the cache miss cost was 70 cycles, but today we're at the order of hundreds and hundreds of cycles. Okay, so prefetcher performance is important. I'm going to quickly cover this, not go into a lot of detail because, but it's important to keep in mind there are multiple metrics that lead to prefetching performance. So accuracy, we discussed. How many prefetches are used out of the sent prefetches? Coverage is what fraction of all the misses that are experienced by the program are actually prefetched accurately. Timeliness is how on time are your prefetches? And there are multiple metrics for this. I'm not going to go into it. But prefetcher design is really science and art in terms of maximizing all of these. And it's very difficult to maximize all of these at the same time. Basically, you may have a very accurate and timely prefetcher, but your coverage may be low. Maybe you may have a very high coverage and timely prefetcher, but accuracy may be low. Basically, you usually can get 2 out of these 3 metrics very high, but 3 out of the 3 is very difficult. Bandwidth consumption is another metric. It's important. This is the memory bandwidth consumed with the prefetcher versus without the prefetcher. Potentially, you can utilize idle bus bandwidth if the bus is idle at a level. Cache pollution is another metric that you should be careful about. Basically, prefetches can lead to extra demand access misses due to prefetch placement in the cache. And this is more difficult to quantify, but this does affect performance, actually, and it's important. So there are many issues in prefetching, but I'm not going to talk about a lot of these issues. There are clearly prefetch throttling. So we talked about actually a lot of these very quickly. There's prefetch throttling. There are issues in multi-core again. How do you actually ensure prefetches of one core do not destroy the performance of some other core, etc. But for that, I would recommend taking the advanced course. And I'll recommend one paper that we wrote in 2007. And the idea in this paper is employed in many existing processors also today. The idea is prefetcher throttling. Throttle the prefetcher if it's not doing well, and make it more aggressive if it's doing well. Then the question is, of course, how do you do that throttling? And I would recommend taking a look at that. And prefetching can actually be very beneficial. I'm going to talk about run-ahead execution a little bit. It's one form of prefetching. But effective prefetching can improve both performance and reduce hardware cost. This is actually data presented by Sun Microsystems engineers, which became Oracle later on. But basically, they said that if you keep the cache size at 512 kilobytes for their commercial workloads at the time, if you do run-ahead prefetching, you get about 40% better performance. But you can actually play other tricks. For example, if you have an 8 megabyte cache size, if you don't do prefetching, you get some performance. If you actually do run-ahead prefetching, you can reduce your cache size to only 1 megabytes because your prefetcher is effective in bringing data into your cache accurately, such that you get with a prefetcher, you can afford to have only a 1 megabyte cache while getting the performance of an 8 megabyte cache without the prefetcher. So you can see that prefetcher can buy you performance while also reducing your hardware cost because you may be wasting. If you keep increasing your cache size, you may not be utilizing your cache really well because they're really reactive approach, and you may not be able to get all of the access patterns in your cache. But if you actually have a prefetcher, you can have a much smaller cache, basically. That's the key takeaways. So it's important to keep in mind that you can optimize the memory hierarchy intelligently if you have a really good prefetcher. And that's what they're showing in this slide. So over here, for example, they're basically saying, instead of building a 16 megabyte cache, just add a prefetcher to a 4 megabyte cache, basically. You get a similar amount of performance. Okay, so let me give you an example prefetcher, run-ahead execution, relatively quickly. since it's close to my heart, and it's also employed in some modern processors. And hopefully this will also give you some potential ideas going into the future on how prefetching is done. And then we will actually switch to virtual memory, but hopefully this will be fun. But basically, when we started developing this prefetcher, our goal was to, the mindset in industry was to actually have large instruction windows. And why do you want that? We already discussed this actually when we talked about out-of-order execution, right? If you're doing out-of-order execution, to tolerate memory latencies, you want large instruction windows, because otherwise you get stalls, right? If your instruction window is too small, it cannot accommodate many instructions in the window. As a result, you stall. And this is going to show that example, basically. Let's assume that you have a small 8-entry instruction window. You get this load instruction. It gets a long latency cache miss, hundreds of cycles. And then you have a branch that's branching based on the load. And then you fetch other instructions that are completely independent. That's why they're green over here in this picture. So they're independent of the L2 miss. They can be executed out of program order, but they cannot be retired. They stay in the reorder buffer and they occupy resources in the machine. Why they cannot be retired? Remember the precise exceptions lecture. You cannot violate precise exceptions, obviously, right? In von Neumann architectures. That's why we have these instruction windows in our processor to begin with. We have these reorder buffers. So the problem is you cannot bring in a younger instruction into the machine and execute it, because now there's no space in your instruction window, as you can see, right? So look at this instruction. That's a load. It may actually miss in the cache. So basically, you cannot bring this instruction into the machine because you don't have space in the machine anymore. Your reorder buffer is full. Your physical resources are full, because this load is really blocking everything. And that's the problem with full window stalls. The processor stalls until this L2 cache misses service. Only after that, you can bring in a new instruction after you retire these red instructions over here, right? So basically, long latency cache misses are responsible for most full window stalls. And I've shown you this picture before in an earlier memory hierarchy lecture, if you remember. We basically did these studies with Intel at the time. We showed that average across many memory-intensive workloads that Intel uses to design its processors at the time, most of the time, the processor is waiting for L2 cache misses to come back from memory. And very small fraction of the time, the processor is actually making progress. So that's called non-stall compute time, because some of this is actually wasted for branch mispredictions also, but we're not going to get into that. In contrast, if you could build a very large machine, 2048 entry instruction window machine, you would reduce the stall time significantly, as you can see. And L2 misses will still be responsible for some stalls, but not as much. So you would actually improve performance significantly if you could build a very large instruction window machine. And that's the goal that people had at the time. So the problem is, as you know very well, out-of-order execution requires large instruction windows to tolerate modern main memory latencies on the order of hundreds of cycles. And as main memory latency increases, we did this exercise, instruction window size should also increase to fully tolerate the memory latency. Remember, we did this exercise when we talked about out-of-order execution and its limits in an earlier lecture. Now, the problem is building a large instruction window is a worthy goal, and people are trying it. That's great. And people actually made a lot of advances in it, but it's still a challenging task, especially if you would like to achieve low power and energy consumption, short cycle time, and low design and verification complexity at the same time. As you increase the size of your window, all of the structures in your out-of-order execution engine should increase, like tag matching logic, load store buffers. We discussed that, how complex it is. And then wake up and select logic, register files, bypasses. And it becomes much more difficult to maintain low energy consumption, power consumption, short cycle time, and low design and verification complexity. So the idea of run-ahead execution is very simple, actually. It's a technique. It's a prefetching technique. That's why we're discussing it, to obtain the memory level parallelism benefits of a large instruction window. And the idea is very simple. As I said, when the oldest instruction is a long latency cache miss, you checkpoint the architectural state. Basically, you save the contents of the register file and the program counter and any other architectural state, architectural registers, not memory, that you need into a special place, because you were going to get back to it. And we enter a special processing mode called run-ahead mode. In this run-ahead mode, the processor speculatively pre-executes the instructions. It's completely speculative execution. It ignores, basically the purpose of pre-execution is to generate prefetches. It ignores long latency instructions. It basically generates prefetches for them, and then it drops them. Basically, it can get them out of the machine so that it can reach other parts of the instruction stream of the program it's executing. So it looks ahead in the program, basically, just to prefetch instructions. It executes ahead in the program. And then when the original miss that caused entry into this run-ahead mode returns, the processor restores the checkpoint, flushes the pipeline, and resumes normal execution. Let's take a look at this pictorially. So ideally, you want perfect caches so that you never stall, right? All loads in your processor program hits. Of course, this is not easy to achieve. Small window machines, when you get to a long latency cache miss, you execute until your window becomes full. Once your window becomes full, you stall. You cannot bring any other instructions into the machine, basically. That's what stall means. And then this miss completes, and then you can continue computation. And then another miss stalls the machine soon after it happens. So real execution times look like this. That's why most of the time the processor stalls, actually. Now, the run-ahead machine is a bit different from the small window machines. It's going to keep the small window, but when it gets to a long latency cache miss, when that becomes the oldest instruction in the window, it's going to checkpoint the architectural state in a clean slate, a clean point. So it's a precise point, basically. And then it enters a speculative processing mode where it generates prefetches for long latency cache misses, but doesn't stall for them. It basically drops them out of the machine. And hopefully it reaches this load 2. And it generates the cache miss because it can compute the load 2's address. And then that miss starts being serviced in parallel with the other miss. And hopefully they go to different banks. And when the original miss returns, we flush the pipeline. That's why you have this red over here. And then you restart execution. You restore the checkpoint, the original architectural state that you had at load 1, as well as the program counter, such that you can re-execute all of the instructions. And you execute all the instructions. And while you're doing that, the second miss completes while all of this is happening. And when you actually get to load 2 in the real program, not speculatively, really, you don't stall. Because the data that's required by load 2 was already prefetched into the caches because you didn't stall. You just speculatively pre-executed the program that is already executing anyway. But instead of stalling, you pre-execute to generate cache misses. And that's the idea. You save a lot of cycles, basically. So let me reiterate. Instead of stalling during a long latency cache miss, it doesn't have to be just L2, right? It could be any cache miss, actually. If you pre-execute speculatively loads and stores and the entire program, actually, and these pre-executed loads and stores, independent of the L2 miss instructions, generate very accurate data prefetches for both regular and irregular access patterns because you're really following the program path. And instructions of the predicted program path are actually prefetched into the instruction and trace cache in L2. So instruction cache also gets primed or prefetched. And hardware prefetcher and branch predictor tables that you have otherwise are trained using future access information. And we found out that this is a synergistic effect as well. So as any idea, this also has advantages and disadvantages, right? Any kind of mechanism in architecture, as you know, or systems or engineering in general has advantages and disadvantages. So let's pick through the advantages and disadvantages of this mechanism. So this is actually a very accurate prefetcher. It provides very accurate prefetches for data instructions, all cache levels, because it follows the program path. It's simple to implement. Most of the hardware is already built in. We're just executing the program just speculatively. There's no waste of context because we're actually using the main thread context for prefetching. We're not actually switching to some other thread, for example, to do the prefetching, etc. Okay, there's no need to construct a pre-execution thread. You may not be able to understand this at this point, but basically, there's no need for you don't need to construct a special thread to do the prefetching for yourself because the existing program that you're going to execute anyway is used speculatively to prefetch. So there's one question over here. How does this work if a load operation is dependent on a previous load operation? How do you prefetch this? So that's an excellent question. Basically, you cannot prefetch that. So for dependent cache misses, this doesn't work. That's why we developed some methods to actually predict the address of dependent cache misses. So that's going to be part of the disadvantages, the limitations over here. So clearly, you execute extra instructions. Instead of stalling, you're executing instructions. If this is useful, that may be good. But if it's not useful, then you have a problem. You're increasing energy. You're limited by branch prediction accuracy because you're following the program path when you're doing prefetching. If your branch prediction is not good enough, you're limited. That's true for any large instruction window machine, actually. Like the question that was asked, you have prefetched. You have prefetched this point, basically. You cannot prefetch dependent cache misses. That's absolutely true. And effectiveness is limited by how many cache misses you can find while you're doing the speculative execution. So memory level, this is called memory level parallelism, as we discussed earlier. How many misses you can service in parallel, essentially. And how many misses you can find also, and also service in parallel. And prefetch distance, basically how far ahead to prefetch, is limited by memory latency. So because you're staying in run-ahead mode, the speculative execution mode, until the original cache miss returns. So you're limited by how far you can look ahead in your prefetching. So there are actually very, very interesting things here. I will also discuss the particular implementations very quickly that are done in Sunrock, IBM Power 6, and NVIDIA Denver more recently. But basically, when we did this study together with Intel, we showed that you can get significant performance improvement compared to a state-of-the-art processor. It's about 22% average across many different workload suites over here. You can see these are different suites like web workloads, multimedia, productivity, server, workstation, and some spec workloads. And you can read the paper for more detail or watch the lectures that I'm going to recommend. But we also showed that you can get the benefits of a large instruction window. So instead of, at that time, the instruction windows are 128 NP or so in Pentium 4, for example. We showed that basically without increasing the instruction window size at all, just adding run-ahead to the machine gets you very close to triple times the instruction window size on average. In some cases, it's better than even a 1024 entry instruction window size. So basically, you get the benefits of a large instruction window, but the prefetching benefits of a large instruction window. And we showed basically that this works even better for in-order machines, because in-order machines do not tolerate memory latencies, if you remember. In-order execution, out-of-order execution can tolerate memory latencies. So we showed that out-of-order execution, you get about 20% performance benefit. In-order execution machines, you get about 40% performance benefit. And you can read more from the paper. This is a paper that was written in 2003. And this was actually my first paper that I wrote in my PhD, if you will. And this is a graph from Sun. I already explained this basically. They were inspired by the idea. They basically implemented it in their ROC processor. And they basically called it Scout execution. But the idea is essentially run-ahead execution with some bells and whistles here and there. And they basically showed very similar performance results. This was an in-order execution machine, and they validated our performance results on their machine, showing 40% better performance. And they actually even show that you can actually get benefits, even if you have a 64 megabyte cache, for example, because run-ahead execution is able to prefetch some random access patterns that are very difficult to get in your cache. And you can read this paper if you're interested in this topic. There are a lot of interesting papers that talk about multiple different ideas. And if you're really interested, this is the real ROC processor that actually has even more ideas in it. And I'm not going to talk about that. So IBM Power 6 also implemented this sort of prefetching. But just to show you, Power 6 actually implements multiple different types of prefetchers. They have a hardware-based stream prefetcher. They also have run-ahead feature. And they both work together well, according to this paper that analyzes both of these types of prefetching. And if you're interested, you can take a look at that. NVIDIA's first 64-bit ARM processor actually had very, very interesting things. One of the things that they did was they did ISA translation, as we discussed with Transmeta, for example. So they basically translated instructions into an internal microcode format. While they're doing that, they added hardware prefetching and run-ahead features. So it's actually very interesting. You can see the processor over here. They have a hardware prefetch engine. They also have a run-ahead engine. But I would actually like to read some of this because this gives you an idea of what they did. So basically, reducing the effects of long cache miss penalties has been a major focus of the microarchitecture, using techniques like prefetching and run-ahead. An aggressive hardware prefetch implementation detects L2 cache requests and tracks up to 32 streams, each with complex stride patterns. They don't tell you exactly what stride patterns, but what I'm guessing over here is if you, for example, have ABC, 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 ABC repeating, these are strides between different addresses, it can actually capture that. And you can see they describe how run-ahead works, and they basically say they get significant performance improvement. So run-ahead complements the hardware prefetcher because it's better at prefetching non-strided streams, and it trains the hardware prefetcher faster than a normal execution to yield a combined benefit of significant percentages, as you can see over here. And again, you can read more over here. So they actually have very, very interesting features that are described in these two papers. Actually, the first paper is more technical. The second paper is a microprocessor report article. And you can read more about how a modern processor does prefetching. And you can see that there are already multiple forms of prefetching. And I would recommend reading it because it actually shows how they actually do micro-coded binary translation so that I can actually so they actually do compilation into a 7-way superscalar processor in a binary translation engine. So they take the ARM code, ARM 64-bit ARM code, they translate it into a 7-way internal superscalar microcode, micro-operation format. And yeah, if you're interested, you can take a look more. So very quickly, not everything works exactly like what you want. And that's true for all ideas. So that's true for the idea that we have developed run-ahead execution also. As I said, there is an energy and efficiency problem if you're not careful because you're executing a large number of instructions speculatively. As one of you mentioned, you cannot parallelize dependent cache misses, so this is not effective for pointer-intensive applications. How do you make it work? So we tackled that issue also in my thesis, PhD thesis. And then there are also irresolvable branch misprediction in run-ahead mode. So if you're executing in run-ahead mode, you're far ahead in the program execution stream. You're speculatively executing. If you get a mispredicted branch that's dependent on an L2 cache miss, long latency instruction, whose value you do not know, you'll be on the wrong path for the rest of the speculative execution. And we analyzed a lot of wrong path issues and tried to solve that problem also. But if you're interested, there are more papers that are written on this topic, and I'd recommend you take a look at those papers. Okay, so this work was recently awarded the Test of Time Award, actually, from the HPCA conference. And when I delivered the talk, I had to retrospect a little bit. But in general, it's good to rethink sometimes what we're doing. So at the time, early 2000s, when I was a budding graduate student, let's say, there was a huge focus on increasing the size of the instruction window. And all of the big companies were trying to increase the size of the instruction window of the machine, which is a good thing, not a bad thing to focus on. But it's always good to focus on some different disruptive ideas also, basically, because there are downsides to increasing the window, of course, designing bigger and more complicated machines. So run-ahead execution was a different way of thinking, essentially. The philosophy was very principled, in my opinion. We talk about principles a lot in this course, right? And our principle was keep the out-of-order core simple and small, and at the expense of some benefits. Give up some of the benefits, like non-memory related benefits, but use aggressive automatic speculative execution. Execute ahead in the main program solely for prefetching purposes. And this turns out it's very synergistic with prefetching and branch prediction methods and other methods that are employed in the out-of-order execution engine, because we're really utilizing the out-of-order execution substrate that we developed in this course to do prefetching when otherwise you would stall. That's the idea. And as a result, a lot of interesting and innovative ideas ensued based on this way of thinking. And there was actually a lot of research that built on run-ahead. A lot of different types of run-ahead were proposed. And you can see certainly the Denver way of doing run-ahead is a little bit different, even though they don't disclose a lot of it. But NVIDIA Denver is based on the run-ahead principles, but they do some things a little bit differently. The Sun Rock is a little bit different also in industry, but there are also a lot of research papers that were written. But we also accredited other work that actually introduced a similar idea early on a while ago in very simple processors. They didn't go all the way we went in terms of the philosophy, but it's a similar idea. And if you're really interested in actually the idea of memory level parallelism, I would recommend reading this one-page paper. This is the entire paper over here that talk about memory level parallelism, basically. Why it's important, how it's important, and why we should design systems, microarchitectures that try to parallelize cache misses as much as possible so that you don't stall for any, or basically you don't actually see, the processor doesn't need to see the stall time for any of the cache misses. We talked about memory level parallelism in last lecture also. Remember, memory level parallelism are like cache replacement. This is another, that work was also inspired by this paper, I would say. And this paper essentially is a philosophy, talks about a philosophy that describes why we should really be parallelizing many cache misses in our systems. Okay, I also presented some slides looking into the future, where I said that microarchitecture is still critically important and fun and impactful. And I think we're seeing it a lot more today with announcements from Apple, for example, M1 and AMD and other systems as well. So there's a lot more to be done. And this was actually a great example of harmonious industry and academia collaboration, because we worked together with Intel quite a bit on this topic. And we still work together with industry in a cooperative way to put out ideas like this into the research domain. And I think this is actually important. This is, I pointed out in my talk, retrospective talk. So these sort of memory problems, prefetching problems, caching problems are very fundamental, and they will always remain fundamental. So you will need to develop new ways of thinking about them. And I think it's really important going into the future we develop new ways, because we'll have a lot more difficulties into scaling problems as we discussed. And we need more fundamental and creative solutions. And this is the citation that we received for the Test of Time Award, and you can take a look at it. But basically, it said that it's a pioneering paper that opened up new avenues in dynamic prefetching, and it affected industry and research. Okay, so I will finish up some slides, but I will also use these last two lectures to motivate you all, since you're just beginning your careers as computer scientists and engineers, regardless of whatever you choose to take, I would recommend following your passion, because whenever you're doing something important, believe in what you're doing. Of course, have good principles while you're doing it. Don't do something wrong, but follow your passion and do not get derailed by people who try to derail you for whatever reason, right? Because they may have some agenda. They may not appreciate what you're doing. They may not be as forward-looking. They may not be as creative, whatever the reason is. Do not get derailed by naysayers. And if you follow your passion and make something happen, then you can have a huge impact in the world. And I see RunAhead retrospectively that way, but we're also doing a lot of work right now, for example, in processing in memory and DRAM, RowHammer, for example, which we're going to talk about again in the next lecture. Those are examples of following your passion. And since you're just starting your careers, I would very much recommend that you don't get derailed by naysayers, because you will see you will certainly have a lot of roadblocks in front of you. If you take them as roadblocks, they will be roadblocks. If you take them as challenges that you either ignore or overcome, then they will not be roadblocks. You will either look past them or overcome them in some way at some point. You don't have to overcome them immediately, right? So do not get derailed, basically, when you're doing something big. And be resilient. So of course, doing what I just suggested requires a lot of resilience, because you have to be careful when you're being resilient. Well, you have to be resilient to be able to ignore some negativity, let's say, right? And I think focusing on learning and scholarship is extremely important. Not everybody focuses on learning and scholarship, but we try to focus on learning and scholarship in everything we do. And I'd recommend this to everyone, because in the end, everything is about continuous learning and scholarship. Learning never ends. Education never ends, if you will. And in the end, the quality of your work, whatever you do, whatever your work is in the end, it may not be computer science in the end, but the quality of it defines your impact. If you do something bad quality, it's not going to be highly impactful in the end. Okay, there's one more question. How is good analysis-based speculative prefetching in hardware kept when using address space layout randomization? Why doesn't this conceptually kill good hit rates? So address space layout randomization doesn't hurt within a process, basically. Certainly you do some randomization, but whenever you do the execution, again, things get randomized. But for example, RunAhead doesn't get affected by it, because the randomization function that's applied is already applied. Okay, but if you try to prefetch across different runs of a program, then of course you may need to be careful about address space layout randomization. I believe you can overcome it, because people have actually found out ways of let's say circumventing ASLR, address space layout randomization, for security purposes. So I think if you really want to do it for prefetching, you can actually do it as well. Okay, but that's a very advanced question that not everybody needs to know the answer to at this point. Okay, so the last slides, I'm just going to point you to some lectures, but basically you can learn more about RunAhead execution. Clearly, I've written a thesis on it, spent 6 years on it and more, actually. And you can learn more about execution-based prefetching in these lectures. And this is the test of time retrospective that I mentioned. But I also have more recommended material on prefetching, which we're not going to be able to cover. For example, we talk about software-based prefetching over here, x86 prefetch instructions, which are very interesting. We talk more about different kinds of thread-based pre-execution. RunAhead is just one form. There are many other kinds of forms. And we talk about a lot of other issues on prefetching, as you can see in these pictures, which we're not going to talk about at this point, because they're more advanced, let's say. But you all have the basics for understanding it at this point, because you're also asking very good questions, as you can see. But I would recommend looking at these different lectures for prefetching, or taking the master's course, or taking our seminar courses. And these are the readings that are copied and pasted again over here. If you're interested, you can take a look at them. Okay, so that brought me to the end of lecture 25A. It took a little bit longer than I expected, as usual. But this is a great place to take a 10-minute break. So we'll take a 10-minute break. We'll be back at 15:34. And then we will start with virtual memory, which we're not going to be able to finish with, but at least we can make good progress on it. And we're going to finish it tomorrow. So enjoy your break. I will see you in 10 minutes. And feel free to ask questions on the chat. I'm happy to answer more of them, since clearly this is an exciting topic that can generate a lot of questions. Okay, let's get started. I think I'll handle one question before we start the virtual memory lecture. It's related to prefetching. One fellow student asks, is prefetching also done between different cache layers, or would it make sense to apply different prefetching for different cache layers? Absolutely, yes. So you can customize the prefetching algorithm and the technique to the layers that the prefetching is targeting. Basically, if you have an L1 to L2, L2 to L1 prefetcher, for example, then you may want to employ a different algorithm than what you would employ from main memory to L4, let's say, for example, or main memory to the processor. So certainly, you may actually use different prefetching algorithms. In fact, in existing systems, there are different types of prefetching algorithms that are used because you can exploit the properties, locality properties, and the information that's available to different layers, of course, right? Because you have different levels of information and different levels of locality, both spatial and temporal, that is present at different layers, as we discussed when we talked about multi-layer hierarchies. So a very good question. Okay, now we're done with prefetching. Of course, I think this is a topic that you can immerse yourself endlessly with. And if you're interested, I think I would recommend looking into future lectures. Now let's move to virtual memory, another fundamental topic that's extremely important. Another idea that was developed in the 1960s. Prefetching was first developed in the 1960s also, actually, in IBM 360 systems, for example. Even earlier, actually. They developed next-line prefetchers for instructions. For example, in IBM 36091 had next-line prefetcher for instruction prefetchers. Basically, whenever you wanted one cache block, the system automatically prefetched the next cache block, for example. Virtual memory was also developed in the 1960s. And while prefetching has evolved a whole lot over the last 60 years, let's say, unfortunately, virtual memory has not evolved as much, I should say, compared to the 1960s. Of course, it has evolved a little bit, right? But not as much. And maybe it requires some rethinking today going into the future. And we will talk about that probably tomorrow if we have time. But one of the reasons why it has not evolved as much is because it's not a microarchitecture level mechanism that's invisible to the software. And prefetching can be, right? If you're doing it hardware level, run-it is completely invisible to the software, for example. But virtual memory is not, as we will see. It's really a system level mechanism, and it's actually dictated by the ISA. And once ISA actually dictates a virtual memory system, it's hard to change it fundamentally, at least. You can keep extending it like what we've been doing and like what we will see in this lecture, but it's going to be very hard to change. And that's what we have been seeing in virtual memory systems, even though some of the things that we do in virtual memory are not as optimal and they cause a lot of overhead. We do it because we need to be backward compatible with the past versions of the ISA, especially x86, for example, but other ISAs have a similar problem with virtual memory today. Okay, okay, that was lecture break, unfortunately, but I should eliminate that slide. Let's eliminate it. Okay. So these are some readings. There, essentially, virtual memory is covered in H&H, Harris and Harris. I'd recommend going through it. I'm going to use some slides from them, but the reading that I recommend on memory systems that we have written is also recommended. And these are two readings that I recommend. This is a survey paper from 1998 that talks about some implementation issues in virtual memory. I think it's good to look at. And then this is a more recent paper that my research group wrote on rethinking virtual memory, such that maybe you can do a better thing than what you can overcome some of the shortcomings. But before we go into the shortcomings, we should really learn about what virtual memory is. And so far, this was a programmer's view of memory, right? The programmer basically can do loads and store to memory. And I've shown you this picture before, right? Actually, I've shown you this also before. Ideal memory, we want zero latency, infinite capacity, zero cost, infinite bandwidth. That sounds great. So far, we've talked about latency a lot, capacity a lot, cost a lot, bandwidth a lot, but we didn't really talk about the programmer's view of main memory as much. And virtual memory is going to be related to capacity, but from a programmer's perspective. And I actually showed you the slide earlier before we started going deeper into the physical memory subsystem, the caching subsystem, etc. I said that we're going to talk about physical addresses, physical memory, but programmer actually sees virtual memory. Now we're going to talk about what that is. Basically, virtual memory allows the programmer, the main memory size is infinite or large enough so that they don't need to worry about it. But in reality, physical memory size is much smaller than what the programmer assumes in many real systems today. That was not necessarily the case in the past. But the system in virtual memory, the system software and hardware cooperatively map virtual memory addresses to physical memory addresses in existing systems. And the system automatically manages the physical memory space transparently to the programmer, so that the programmer doesn't worry about running out of the main memory space. And that's one huge benefit of virtual memory, one of the reasons why it's there. The programmer should not worry about managing, worry about running out of physical memory and managing the data and code blocks such that you don't run out of physical memory, basically. The system transparently provides that support, both in hardware and software. So this is one of the most successful hardware-software cooperative design ideas that has permeated all our computing systems today, essentially. Almost all our computing systems today. Almost all computing systems have virtual memory. And even if they don't have today, 10 years from now, they may have virtual memory, because some accelerators may not have virtual memory. But as they become more general purpose over time, you will need this sort of support to make programmers' life easier. So basically, the big benefit, as we discussed earlier, is programmer does not need to know the physical size of memory, nor do they need to manage it. So a small physical memory can appear as a huge one to the programmer. As a result, life is easier for the programmer. Of course, every idea comes with a downside. Now we have a more complex system software and more complex architecture to do this automatic management for the programmer. And this is a classic example of the programmer architect, micro-architect trade-off, as we discussed. You try to make life easier for the programmer, but the hardware designer's life becomes harder. In this case, system designer's life becomes harder also to maintain this illusion that we're going to talk about. So we have already discussed the benefits of automatic management of memory between the caches, right? And you can imagine that this just extends to main memory as well. Basically, if you look at main memory, programmer now doesn't need to deal with physical addresses. And they don't need to deal with running out of space in the physical memory address space. That's the key benefit. And we'll talk more about that. And also at the same time, each process has its own independent mapping of virtual to physical addresses. Each process has a different virtual to physical translation mapping. As a result, the processes can be isolated from each other in physical memory. And the programmer doesn't need to worry about that sort of isolation also. So there are two benefits. One is the illusion of infinite memory, if you will, and the second is isolation between processes. But actually, I'm going to show you more benefits over here. So basically, having these properties enables code and data to be located anywhere in physical memory. So you can relocate the code and data at different places. You can flexibly locate data. For example, a huge array, a 1 gigabyte array, does not need to be consecutive in memory. You can chunk it does not need to be consecutively allocated in the physical memory space, right? You can chunk it into different pieces, and you can basically use available parts in the physical memory, as we will see. Isolation and separation of code and data of different processes in physical memory is enabled, as I mentioned, because each process has its own independent mapping of virtual to physical addresses. This leads to protection and isolation between different processes that are running concurrently in the system. So it enables multi-programming. One of the reasons why virtual memory was not present in very early systems is because those systems were not multi-programming systems. They were belonging to a single program. You were not executing other programs concurrently. But today, almost all systems are multi-programming systems. And if you want protection and isolation, virtual memory is one way of doing it. Code and data sharing between multiple processes also becomes easier. This is called sharing in general, because by just having a mapping mechanism, you can map different virtual addresses in different programs to the same physical address so that they can share data, for example. So this mapping mechanism between virtual and physical addresses enables multiple benefits, as you can see, and as we will see in a bit more detail. So let's take a look at a system with physical memory only. This is what we have assumed so far, basically. CPU, load and store instructions, generate physical memory addresses. This could be an accelerator also. It could be any computation unit. Whenever you're accessing memory, you're really accessing directly physical locations, right? So examples, early supercomputers, certainly most Cray supercomputers, early personal computers, many older embedded systems are like this. Many modern systems, except for accelerators, actually have virtual memory today. In fact, even GPUs are moving towards having more sophisticated virtual memories today, going into the future. So basically, why do we want it then? Basically, the problem is physical memory is of limited size because of cost, right, reasons, as we discussed. What if you need more? Should the programmer be concerned about the size of their code and data blocks fitting physical memory. What if the code and data doesn't fit physical memory? What does the programmer do? Does the programmer need to explicitly bring the data from the disk to the physical memory? In fact, that's what people used to do in the past when virtual memory automatic management was not present. This is called programming using overlays or overlay programming. They used to basically overlay while they're operating on some code inside physical memory or data inside physical memory, they would bring or prefetch, let's say, data from the disk into physical memory. And this is a lot of effort on the programmer's end. And it was a mess, basically, for average programmers in general. And that's what I said, basically. Should the programmer manage data movement from disk to physical memory? Probably not the average programmer, at least. On top of this, multiple programs may need the physical memory concurrently at the same time. Should the programmer make sure all processes, meaning different programs, can fit in physical memory? How do you even do that? Because the processes may not belong to a single programmer, right? The processes may belong to different people that are sharing the machine. And this is not an easy task. And this is also one of the reasons why early operating systems were developed to distinguish between different processes and schedule them, deschedule them, etc. And virtual memory was a synergistic idea to provide protection and isolation between these different processes. And then the next question is, and also enable the fitting of these different processes to physical memory. Should the programmer ensure two processes do not unintentionally or incorrectly use the same physical memory portion? Because you may be executing two processes. Clearly, the processes normally do not communicate, right? If you're operating on your array, if some other program should not be writing or reading your array, right? Clearly, that's a big security problem, and also reliability, dependability problem, because if you're operating on some array and somebody else is modifying your data, even though they were not supposed to, then you have a protection and isolation problem. And it's very difficult for the programmer to ensure that without any system support. And virtual memory is one way of actually helping multiple programs execute at the same time, concurrently, or over time also. But concurrently is the harder problem, of course, right? And also, one other issue is ISA can have an address space greater than the physical memory size. For example, many ISAs today have a 64-bit address space with byte addressability, but clearly we don't have 2 to the 64 byte memories. That's huge, right? And what if you do not have enough physical memory? Then your 64-bit address should not be physical, right? Or you need to translate it in some way, which brings you to some indirection and mapping that is similar to physical memory, similar to the notion of virtual memory. So these three reasons are the reason why we do not have this picture, and we're going to modify it such that we go through a translation layer. CPU will generate virtual addresses, and we're going to map them to physical addresses. Okay. So basically, let me talk a little bit more about the difficulties of direct physical addressing in the picture that I showed. Programmer needs to manage physical memory space if you have direct physical addresses, meaning CPUs, loads, and store instructions directly reference physical memory locations. And this is clearly inconvenient and difficult, and it's bug prone also. And it's more difficult when you have multiple processes, because now you need to manage the physical memory space across multiple programs, which is even harder because they may be programmed by different programmers. So it's virtually impossible, basically, at this point. It's difficult to support code and data relocation because addresses are directly specified in the program. You basically say physical address 5. But what if that physical address 5 is also referenced by some other program, for example? Or what if you want to relocate it for whatever reason, right? And it's not easy to do this, basically, if you have direct physical address. As I said, difficult to support multiple processes. You do not have protection and isolation between multiple processes because everybody has the same physical address space if you have direct physical addressing. And as a result, you cannot distinguish between them. So you need to have some sort of protection and isolation mechanisms. And virtual memory provides one way of providing protection and isolation. There are other ways like segmentation, which we're not going to talk about. But essentially, segmentation essentially provides different physical addresses to different processes. That's it. It becomes difficult to share code if you have segmentation. You need to have different sort of segments, but it's actually used today in some systems, but as a legacy. For example, x86 64 architecture has segmentation in it still, so that it can separate processes in an early, very primitive form of protection and isolation. Processes have different segments, for example, so that they're isolated in physical memory. But virtual memory actually supersedes the protection and isolation that's provided by segmentation. So that's why we're not going to discuss segmentation, but you may hear the term segmentation but it's essentially a way of isolation between different processes and different pieces of code in general. So, but segmentation makes it a bit harder to share physical memory space without problems. Basically, multiple processes sometimes want to share the same physical data. For example, you may have shared libraries. You may have shared code that's executed by different programs. In that case, you don't want to replicate things. In fact, it causes coherence problems probably if you replicate things. You would directly want to share code and data. And an additional level of indirection actually helps. Direct physical addressing doesn't help this. And then I think this is actually similar to this last point. Difficult to support data and code sharing across processes if you have direct physical addresses. Different processes need to reference the same physical address in some way, and it's not easy to do because they have to somehow coordinate different physical addresses. And how do you do that, right? How does programmer A know to use the same physical address as programmer B? You need to have a central database, and that becomes very, very cumbersome to maintain. Okay. So there are a lot of difficulties, basically. So that's why virtual memory was developed. And the idea is very simple. It has multiple benefits. But the main benefit, the idea is to give each program the illusion of a large address space. Oh, sorry about that. A large address space while having a small physical memory. Infinite memory, I would say. Let's say that's the illusion. So that the programmer does not worry about managing physical memory within a process or across processes. And that gets rid of all of the downsides that we discussed in direct physical addressing. Now, a programmer can assume they have an infinite amount of physical memory. Now, clearly, it's not infinite, but for all practical purposes, hopefully infinite. Hardware and software cooperatively and automatically manage the physical memory space to provide the illusion, essentially. And the illusion is maintained separately for each independent process. Each independent process has its own mapping. So the basic mechanism is indirection, essentially. Basically, as opposed to having direct physical addresses, we're going to have indirection and addressing main memory. So the address generated by each instruction in a program is a virtual address. So it's not going to be a direct physical address. In other words, it's not the physical address used to address main memory. This is also called the linear address in x86, basically. Virtual address is the linear address in x86. You will see some pictures of it later on. And then we will have an address translation mechanism that maps this virtual address to a physical address. So it's going to be indirection. It's going to be additional latency, and we're going to try to solve those latency problems. And this physical address is called a real address in x86, as we will see also. And this address translation mechanism is implemented in hardware and software together, as we will see. Okay, so this is from the chapter that I recommended that you read. Essentially, the conceptual view is that you have illusion of large separate address space per process. And this is a picture from the handbook. Essentially, you divide the virtual address space of each process into chunks. In this case, 4 kilobyte chunks. 4 kilobyte happen to be a good granularity that people use to do this mapping. And you can see that your virtual address space can be huge. In this case, 48 bits, 256 terabytes in a byte addressable system. And each process has its own virtual address space that's completely separate. But then there's a mapping mechanism that takes each process's virtual address space and maps it to the real physical address space on the system, which can be 8 gigabytes in this case. And you can see that there's a mapping mechanism that needs to happen so that you can actually have your data in physical memory when you actually really need to access it. So basically, this requires indirection between virtual and physical, and a mapping mechanism between virtual and physical spaces. So there are two ideas, indirection and mapping. Indirection requires the mapping, of course. And this is the view that we get now. This is a system with virtual memory. It's a page-based virtual memory. Basically, virtual memory is divided into chunks that are called pages. And in this case, it's 4 kilobyte chunks. Today's systems can be divided into multiple different granularities, as we will discuss. But 4 kilobytes is a good assumption for now. And basically, CPU generates virtual addresses. And there is a mapping table called page table, as we will see more of soon. The hardware and software cooperatively actually converts virtual addresses into physical addresses via an OS-managed lookup table. So this lookup table called page table is managed by the OS, but it's accelerated by the hardware. Hardware looks up the page table and then converts the virtual address to a physical address. And this way you can enable multiple things. You can basically do the mapping, but you can also say, oh, this virtual address that I'm addressing right now is not in physical memory, so let me bring it from physical memory. So it may be actually in disk. So if it's not mapped in physical memory, it's probably in disk, or that needs to be indicated, of course. And then you can map it. Basically, the operating system and hardware cooperatively can bring it from the disk into the main memory, physical memory. This is called a page fault, and we will discuss page faults in this lecture also. Okay, so this way, programmer doesn't need to manage physical memory. From the programmer's perspective, everything is virtual, and the system makes sure that the data that's referenced by the program is brought from the disk into the physical memory before it's being operated on. And if physical memory is small, that's fine. The system basically manages the data and the mappings such that it brings the data that is really needed by the programs at this point and keeps it in the physical memory, and everything else goes back to disk. So now we're having a multi-level memory hierarchy, very similar to the caching system, as we discussed, managed by the operating system, as well as the hardware, as we will see concurrently. But the operating system actually plays a huge role here. But you do need the hardware to transfer the data as well, as you can see. But basically, this physical memory over here is a cache for the disk from the programmer's perspective in this case. And whenever you need the data, the automatically managed demand paging system brings the data into the physical memory from the disk. Okay, so hopefully that's clear. There are many issues over here that we will discuss in a little bit. But this is a page-based virtual to physical mapping. You can see each process may have a 4 GB virtual memory system. This is actually a simple example. But today, actually, we have 256 terabyte type of virtual memory, even larger, actually, depending on your address bits. It could be 64, but x86 uses 48, I think. They may have extended recently again. Who knows? But basically, you have two processes in this example. Physical memory is 16 megabytes, small. We divide the process into pages. We divide the physical memory also pages. I'm also going to call them frames later on. And you have virtual pages from the process perspective and physical pages or physical frames from the main memory's perspective. And then there's a mapping between done through the page tables. And page table is the lookup table to understand that mapping and also manage the mapping and also manage the hierarchy between the physical memory as well as the disk. Okay, so we're going to look at multiple issues here. There are at least 4 issues, at least 4 major issues, let's say, in indirection mapping. One question is when to map a virtual address to a physical address. I'm not going to delve a lot into this, but basically, when the virtual address is first referenced by the program, makes sense. Basically, it's demand paging. But of course, you can do prefetching as well. You can apply the same principles of prefetching that we discussed from the disk into the physical memory and change the mappings. Obviously, you can do that, but we're not going to talk about that as much. Modern systems do both. They do demand-based mapping as well as prefetching across the memory hierarchy, across the disk and physical memory. What is the mapping granularity? That's important because this determines the page table size. Is it every single byte? Is it kilobytes? Is it megabytes? Is it gigabytes? Is it multiple granularities? We will see that existing systems use multiple granularities because if the programmer knows how to map, that's great. If you can exploit the spatial locality in mapping, then you can reduce the page table size, right? But if you cannot exploit the spatial locality in mapping, if you map 1 gigabyte chunks, then there's a problem, right? If you access only 8 bytes within 1 gigabytes, that doesn't sound good, right? You need to bring in all of that data into the physical memory, or at least you need to have the space in physical memory for all of that data that's at the mapping granularity. Then where and how to store the virtual to physical address mappings. This is important. Page table clearly is one example, but how do you actually do it? Operating system data structures. Do you also store it in hardware? Do you cache it in hardware? And we will see that the answer is yes. Do you do it cooperatively between hardware and the software? And we will see that the answer is yes. And then the next question is what to do when the physical address space is full. Now you may know the answer to this. Basically, evict an unlikely to be needed virtual address from the physical memory. And this makes sense because physical memory is a cache for the disk from this perspective, right? Basically, you can manage physical memory similar to the principles that we have seen for cache principles. Okay, so let me introduce some more terminology. Virtual address space is divided into pages so that we can manage the large translation table sizes. You can map every single byte to another byte, but this doesn't exploit the locality in translations. And also, this doesn't make your translation table small. That's why we need to have large enough pages. And 4 kilobytes is a good size to start with, but people are actually increasing the size of these pages. Physical address space is divided into equally sized pages. These can be called frames. We're going to call them pages also in this case. You can call them both. A virtual page is mapped to a physical frame in the page table if the page is in the physical memory, or it's mapped to a location in disk otherwise, right? If it's not inside the physical memory. If physical memory is not allocated, if the virtual page is not referenced and the physical memory is not allocated, then it's in disk. If an accessed virtual page is not in memory but on disk, the virtual memory system brings the page into a physical frame and adjusts the mapping. This is called demand paging. You may have heard of this clearly. And page table is the table that stores the mapping of virtual pages to physical frames. Essentially, that stores the translations between virtual pages to physical pages, let's say. So essentially, in other words, physical memory as a cache is a cache for pages stored in disk, right? In fact, it is a fully associative cache in modern systems. A virtual page can potentially be mapped to any physical frame, as we will see in a little bit. And similar caching issues exist, as we have covered in caching. That's why we covered caching earlier than virtual memory. But basically, you need to do the placement, meaning where and how to place or find a page in physical memory. You need to do the replacement, what page to remove to make room in physical memory. You need to decide the granularity of management. What's the size of the page? Large, small, uniform. Now, since there's software management involved here, we actually have multiple granularities in existing systems, which we did not have in a level of cache. We need to take care of the write policy again. What do we do about writes? When we modify a page in physical memory, do we write it into the disk every time as well? Bad idea, because disk is so slow, right? So usually physical memory is a write back cache for the disk, right? That's why you need to keep track of modified blocks or modified pages in physical memory as well. So physical memory is no different than a cache, essentially. In fact, you can do this analogy. Cache block is a virtual memory page. Cache block size is the virtual memory page size. Cache block offset is the virtual memory page offset, as we will see. A cache miss is a page fault in virtual memory. Cache index and tag bits are decided by the virtual page number in virtual memory, as we will see. Okay, so page size is the mapping granularity of virtual to physical address spaces. We will see different page sizes soon. This also dictates the amount of data transferred from hard disk to DRAM at once, or amount of data that needs to be allocated in physical memory. That's why having a large page size is dangerous, because you may need to transfer a lot of data, even though you may not be using it. This is very similar to a cache block, right? We said the same thing for cache blocks. This determines the page table size. Page table is essentially the tag store, right, for the cache. I mean, I didn't say this explicitly over here, but we can add page table as potentially a tag store for the physical memory. Page table is the table that stores virtual to physical page mappings. It's really a lookup table used to translate virtual page addresses to physical frame addresses, and where to find where the associated data is. So this is essentially, you can think of the translation table or a tag table as well, from the cache terminology, of course. And then address translation is the process of determining the physical address from the virtual address. So let's go over some examples of this. So basically, remember this, I showed you this picture in the memory hierarchy. I said we want to build a memory hierarchy because with good locality of reference, memory appears as fast as this cache, but as large as this larger entity, main memory, for example. And the same thing applies for cache and disk, or physical memory and disk as well. Basically, the goal is to be as fast as this physical memory while getting the large capacity, infinite capacity from the programmer perspective as a disk. And hopefully most access is hidden in physical memory, and programs see the large capacity of virtual memory. And this is the example address translation. Basically, you have a virtual to physical address mapping that's determined by the page table. And this is how you do the translation, basically. So let's assume that this is from your book also, so you can read your book for more details and detailed explanations. But they basically look at a 31-bit address space. It's 2 gigabytes, and a 27-bit physical memory space. I think it's 128 kilobytes or megabytes, sorry. And basically, the translation happens at the page granularity. So at the bottom parts of the bit, page offset, this is very similar to the byte in block in caches, for example. It's 12 bits. That's 4 kilobytes, right? So page offset doesn't get translated during the translation process, but virtual page number gets translated into a physical page number or physical frame number. And that translation is done by the page table, essentially. So let's take a look at an example, a virtual memory system. So a virtual memory size is 2 gigabytes. I showed you earlier, actually. You have 31 bytes. Physical memory size 227 bytes. Page size 4 kilobytes, 212 bytes. Many systems have 4 kilobyte pages today. Some of them are 8 kilobyte pages. Organization looks like this. Virtual address should be 31 bits. Physical address should be 27. Page offset should be 12 bits. Now you can compute the number of virtual pages in virtual memory. It's 2 to the 19, as you can see. So virtual page number should be 19 bits. And physical pages in physical memory, which is 2 to the 15, by dividing the physical memory size with the page size. And physical page number is 15 bits. So these are very easy things. And this is the mapping table, basically shown in your book also. Basically, we don't explicitly show the page table. We're going to see that in a little bit. But essentially virtual addresses are mapped at a page granularity. That's why you look at virtual page number to physical addresses, and you have the physical frame number, right? So offsets don't change, page offsets don't change during translation, but the virtual to physical translation in terms of page numbers happen. So you can see that some of them are in physical memory. The blue ones are in physical memory. The non-blue ones are not in physical memory, and they're mapped to disk. Okay, so how do we translate addresses? Page table has entry for each virtual page number, essentially. It has to. Otherwise, you cannot translate an address, and otherwise you won't be able to support virtual memory. Each page level entry has a valid bit, very similar to a cache again. And this basically specifies whether the virtual page is located in physical memory, whether the virtual page is cached in the physical memory, essentially. If not, it must. If you get an invalid bit, if the page table entry that you're accessing is invalid, you need to fetch it from the hard disk. Basically, that's a page fault. Then you need to have the physical page number inside the page table entry. This basically specifies where the virtual page is located in physical memory. And also other bits like replacement policy bits, dirty and modified bits, like in caches. And we also will talk about protection, access control in the next lecture. So you need to have permission and access bits in many page table entries. So this looks very much like a cache, as you can see. Valid bits and a tag, if you will, right? Okay, so let's take a look at the page table for our example earlier. This is the page table, basically. For each virtual page, you have an entry that has a valid bit. In this simple case, it just has a valid bit and the mapped physical page number if the page is in virtual memory. If the valid bit is 1, you'd better have the correct mapping. If the valid bit is 0, then that means it's in the disk, right? So let's take a look at some example translations quickly, and then we're going to conclude and go for the next lecture. Essentially, going over here, and these are examples from your book also, so you can follow from your book if you need to go somewhere at this point. But basically, this is how a virtual address is translated. Virtual address is 31 bits, as I said. The bottom 12 bits is offset. We need to access the page table for that virtual page number. So a page table is stored in physical memory. And this is going to be an issue later on that we're going to solve. But page table has a page table base register. And each page table entry, as I said, stores each virtual page number corresponding valid bit and physical page number. If valid, physical page number specifies the valid map location in physical memory. Otherwise, it says it's in disk, and it may contain information on how to fetch it from the disk, for example. But page table is located at physical memory. We're going to question that later on. But it's at a physical memory address specified by the page table base register. This is part of the context of a process. So each process has its own page table base register. Whenever you do a context switch, you need to modify the page table base register so that you reference the correct page table, right? Because each process has its own view of virtual memory, right? And the translations. Okay. So you basically index the page table using the virtual address that the program has generated. In this case, virtual page number is 2. So basically page table base register plus the 2. So we basically index a second entry of the page table. And it happens to map to this location. It happens to be valid, as you can see. Page table provides a valid bit and the PPN, physical page number. If it's valid, then you get the physical page number and append it to the page offset, and that's your physical address. So that's how you do the translation. If the page table entry at the virtual page number coming from the virtual address is valid, you basically replace the virtual page number with the physical page number that's inside the page table entry, and that's your physical address concatenated with the page offset. And now you can access your cache hierarchy. Okay, sounds perfect, right? So page offset bits do not change during translation, as I showed you earlier clearly. Okay, so let's do some examples. I mean, you can do this on your own also, but and also there in your book as well. But basically, the question is, what is the physical address of virtual address 0x5f20? And by now, you know, we have the assumption that last 12 bits are the page offset, top 19 bits are the virtual page number. The first step is, how do you determine the virtual page number? You first need to determine the virtual page number, and based on that, find the page table entry containing the translation for the corresponding VPN. And the hardware needs to do that in the processor. So hardware needs to look up the page table entry at the address corresponding to the virtual page number in the page table of this process. And how does the hardware calculate that address? It basically takes the page table base register, which gives you the base address of the page table. It adds to it virtual page number times the size of a PTE, page table entry. And that's the memory location memory address of the page table entry that houses the translation for the virtual address that has that virtual page number, right? That's the idea basically. And the hardware needs to generate a memory access to do the translation, as you can see. So there's going to be overhead for us because remember, we said indirection. Indirection means another memory access to do the translation. So we need to access the page table, which is in physical memory, to get the translation for a virtual address so that we can access the memory at the physical address corresponding to that virtual address. That's the idea over here. So this is the address that you need to access in physical memory to get the translation. Page table base register plus virtual page number times the size of a PTE. Okay. Size of a PTE can be 4 bytes, 8 bytes, depending on the implementation clearly. This needs to be specified in the ISA also. So in this case, virtual address, it looks like this, 5F20. So bottom 12 bits are page offset. The top 19 bits correspond to virtual page number 5. So we need to index virtual page number 5, get the entry 5 in page table. And if you look at entry 5, if you do the memory access, page table base register times 5 times the size of a PTE, page table entry. It could be 4 bytes or 8 bytes, whatever. It doesn't matter. You do the memory access here. You get this page table entry. It's valid. That's great. And it has a physical page number. Now you can actually say, oh, this is in physical memory. And the physical address is 0001 F20. That sounds good, right? I mean, this is, I just spent more time explaining it so that you're more comfortable with it, but you can read the paper also. You can read the book also. So there's one question very quickly. Do caches also use virtual memory? We're going to get back to it. We're going to get to it tomorrow, not today. But so far, assume that caches use physical memory. But L1 caches are special, and we may actually want to do something special with them because we may not wait. We may not want to wait until the address translation happens, but patience, we're going to get to it. Okay, let's take a look at another example in this particular page table again. What is the physical address of this virtual address? 0xF73E0. We do the same thing basically. Chop up the virtual address into page offset and virtual page number. Ignore the page offset for now. That's not going to change during the translation. Virtual page number now we know is 7. So if you look up entry 7 in the page table, the processor does this by accessing memory, and it finds out page table entry has a val bit of 0, which means that the page, the virtual page that we're looking for is not mapped into physical memory. So the virtual, and this is called a page fault. So the virtual page must be swapped into physical memory from disk. And now the system needs to take some action so that it brings the virtual page from disk into physical memory. It adjusts the mapping afterwards to 1 and then changes the physical page number over here and then does the translation again at that point. And then you can get the translation. So at this point, just by accessing the page table, you cannot do anything because virtual address is not mapped to physical memory. So the answer is you don't know the physical address, basically. It's a page fault. So we're going to cover some issues, but just to prime you for what's coming next in the next lecture is page table size is problematic. So assume a 64-bit address space over here. You can see page offset, assume 4 kilobyte pages in this case. So your virtual page number is 52 bits. And assume that your physical address is 40 bits. So you need 28 bits physical page numbers and 12-bit page offset. So page table does a 52-bit to a 28-bit mapping, basically. 52-bit virtual pages are mapped to 28-bit physical pages. How large is the page table? Well, I didn't give you everything over here, but you definitely need to have 2 to the 52 entries. Assume that each page table entry is 4 bytes, which is a stretch because it's going to be actually bigger than 4 bytes because you need to store some other information than just the physical page number and the valid bit. So 2 to the 54 bytes. That's a lot of memory, right? And that's just for one process. You don't want this to be in physical memory because your physical memory, this is larger than your physical memory, right? We just said that your physical memory is 40 bits, 2 to the 40 entries. You cannot store a 2 to the 54 byte page table in it. This doesn't make sense. And this is just for one process. What if you have hundreds of processes? Now it's impossible to have actually the entire page table in physical memory. And we're going to tackle this issue tomorrow. And also, the process may not be using the entire virtual memory address space as well. That's going to be important and interesting as we talk tomorrow. But I think this is a great place to stop, because now we've come to interesting challenges, because we learned the basics of virtual memory, which you can also read in your book. But tomorrow we're going to tackle some challenges like page table is large and page table translation is slow. And we're going to solve those challenges. And hopefully we're going to go into even more interesting challenges. So I'm going to stop here today. If there are any burning questions, I'm certainly happy to take them. I think there were a lot of good questions that were asked in this lecture, so it's fine if we don't have any questions. Tomorrow is going to be our last lecture, and we're going to finish up virtual memory, and we're going to have an epilogue. And feel free to prepare questions for tomorrow also. So hopefully we'll have an interesting last session talking about exciting topics. So until then, have a good evening, and I will see you tomorrow. Take care.